All right. So since we looked into the p-n junction and the formation of depletion layer, the next thing that follows is the chapter 2 on the diodes itself. This entire chapter 2 and 3 will talks about diodes and their applications. That's chapter 2. Special purpose diodes is chapter 3. So that's where we talk about uh, different types of diodes. So the diode throughout that we will be discussing, this diode has a name, even though it comes under the category of diodes. This is usually referred as rectifier diodes. So whenever we say rectifier diodes, that's basically a diode which will have the same exact characteristics that we just talked about as of a p-n junction. But they usually go by the name rectifier diodes. So like when we're purchasing the diodes, there are various categories of diodes. One of them is rectifier diodes. Chapter 2 will completely be, whenever we say diode, we are actually referring to a rectifier diode. And there are huge list of other diodes, such as, remember the LED I mentioned, which is called as light emitting diode. That's one type of diode. So we have some diodes which can operate under infrared. Like for example, if you have your, like in the TV remotes, in the front of the TV remote, you see like a little light type of filament. That's actually a diode. It's an infrared transmitter. In the TV, you have another diode that's an infrared receiver. That's also a diode based off of the infrared. You have another type of diode called as a Zener diode. That's one type of diode. There is another type of diode called as a pin diode, and I can keep on going. There are huge variety of diodes are available for various applications. But the one that if we simply say diode, we are actually implying that it is a rectifier diode. Rectifying is an application. Remember AC to DC I mentioned before. One of the application of the diodes is in power supplies, where you convert AC voltage to a DC voltage. That process is called as rectification. That's why the name rectifier diodes, those diodes are used for that purpose. So this chapter will talks about what is the diode is, which is, as I said, it's nothing more than a p-n junction. But we will see how it will operate under forward bias condition and under reverse bias condition. So what will happen under forward bias? What will happen under reverse bias? How to mathematically analyze it. That's where you will see some formulas on how to calculate currents under forward bias, under reverse bias conditions. So what is a diode? Again, a diode is nothing more than a simple p-n junction. So you take a piece of either silicon, germanium, but you can take a piece of semiconductive material doped half with p region, half with n region. Remember, that's what a p-n junction is, correct? But we're not going to call the terminals as p-type and n-type. The diode has two terminals. They are called as anode for the p region, cathode for the n region. So that's what the terminals of the diode is, anode and cathode. So again, anode is depicting the positive side of the diode. Cathode is implying the negative side of the diode. So this is the circuit symbol for the diode. Again, rectifier diode too. So you see, it's like a triangle facing this way. Of course, you can rotate it, you can draw however you want, but a straight line right here. That's the symbol for diode. So the anode is This side is referred as the anode. That's the P side. Whenever you see that flat line right here, that's a one single line, so that's going to be the cathode. This is how we draw on the circuit diagram. But how do you visually see a diode and able to tell which side is positive and which side is negative? This is one example to show. This is one of the type of diode we will use in the lab. You see, one side cathode is always being marked on the diode with a band or a tap type of feature. So in here you see right here there is a silver color band right here, correct? That shows that is the cathode. Sometimes it may not be silver, sometimes it may be a black color. But as long as you see some sort of mark on one side of the diode, that mark actually shows you it's a cathode. That means the other side would be the anode. It's just a mark. It doesn't represent anything. Depends on the manufacturer. Someone will go with silver color mark. Some uses black. Because there is another diode that you will see. The whole diode will be orange color. But there is going to be a black color mark on one side. That means that black color mark is the cathode. If everything looks good, your circuit is not working as it's supposed to, probably you put the diode backwards. The diode. Yeah, yes, that is correct. Anode is the positive side, which is the P-type semiconductor. Cathode is the negative side, which is the N-type semiconductor. Right? So this is what the circuit symbol is. That's how we draw a diode. And this is how visually it looks like of one type of diode. So whenever you see silver color mark or black color mark, that indicates the cathode. So biasing, we kind of talked about this one before. What is biasing? Is applying external DC voltage. Again, biasing means it's only DC voltage. Applying external DC voltage needed to make the device work. There are two types of biasings or exist. One is forward bias and one is reverse bias for the diode. So what happens under forward bias is, forward bias allows the current flow through the junction. Forward bias allows the current flow through the PN junction, whereas reverse bias will prevent the current flow through the PN junction. Again, how it will do that, we'll see in a bit, but that's what it means. So whenever we say forward bias, we automatically implying that current will flow through the junction. Again, how much current? That depends. So whenever we say reverse bias, current will be prevented by the PN junction, by the same PN junction. Again, this stands true even when we get into transistors, because transistors also have PN junctions, but not one. Transistors do have like more than two or more. But it's still the same exact thing. When we say forward, it will allow the current flow. When we say reverse bias, it prevents the current flow. So let's take a look at forward bias and how can we make a diode forward bias. So observe the PN junction at the bottom. This is bias voltage. Again, bias voltage is nothing but the supply voltage. They say bias because that's the voltage needed by the junction. Remember that biasing is the term we use for the DC voltage, correct? So that's why it's simply stated as a bias. So you see that the construction of the forward bias, the positive side of the voltage source, you see it's a positive and negative. The positive side is towards the P-type, whereas the negative side is towards the N-type. You see there is a resistor right here. In a lot of applications, a resistor is used in between. It's called as a limiting resistance in order to prevent, not to damage the diode itself when it is forward biased. Because remember that when it is forward biased, the current will be allowed, correct? So in order to prevent the damage for the diode, a current limiting resistance known as, it's a resistor pretty much. You see the subscript is telling you it's a limit. So it is to prevent the damage to the diode. If you having excessive currents, again, a lot of applications we do in the lab, you're not going to damage the diode. But if you have high voltage, high current applications, it's just a safe measure of having a resistor. So limiting resistance is just to protect the diode. Remember that the bias voltage must be greater than whatever the barrier potential is. For silicon, it's 0.7. For germanium, 0.3 volts. Unless otherwise specified, we always use silicon. For example, if you see a circuit, if it doesn't know, if it doesn't give you whether it is silicon or germanium, by default it is silicon. If it is germanium, it will clearly specify to you that it is a germanium based diode. But as I said, throughout this course, we use silicon. So that's the connection wise for forward bias. But what will happen? So why forward bias allowing the current? Right, so let's take a look at that. So when you have forward bias, we know the current will flow. So this is forward bias, correct? So we take the positive and we apply negative, correct? So that's a forward bias condition. Again, always remember that whenever you say forward bias, current will be there. It doesn't matter how much voltage you put here. But the question is the current is appreciable current, meaning that can I use that current to do something else? Only that happens when this one is at least. If you have more than 0.7 volts or even at least 0.7 volts, then you have a full flow of current needed. But if you say, let's say I have only 0.6, you will have some current, not zero. Are we clear? It's not going to be significant enough to say I have a fullest current in the circuit, right? You will see some curves that shows the diode behavior. There you will see a little bit more in detail on what's the shape of the curve is. But always remember that whenever you are forward biasing, even if you have 0.4 volts here, there is a little bit of current will be there. But it's not enough to do what the purpose of diode is, right? But let's say, for example, you have enough voltage. So all the electrons will be pushed through, because remember this is the voltage source. Oh, did I do something? All right, so let's say we have enough voltage. So all the electrons from the negative terminal of the battery will be pushed through towards this direction, correct? So this is already N region, right? That means you are already having very rich in electrons here, correct? So you have already rich in electrons and you are pushing more electrons. So electrons to electrons, what will happen? Repulsive force, right? So all these electrons will be pushed to go across the barrier. If you have enough voltage of 0.7, all of these electrons will be pushed across the barrier. But on the other side, what we'll have? On the other side, we have a positive. So all these electrons that is being pushed will be attracted towards the positive terminal of the battery. Right? So that's the electron flow. So you have some current in the junction. Again, you can have a full current if you have at least 0.7 volts, because that will counteract the already developed barrier potential of 0.7 volts. Then you can operate it whatever the application you want to operate as. Again, we're only talking about how to use the diode at this moment. How to forward bias a diode, if so, what happens. Right? So what application of it, that's coming after next class. We will talk about, we will start applications. Okay, if diodes conduct current, what can I do with it? Right? So that will coming later. But when it will does that, when you apply at least 0.7 volts where positive is connected to the p-type, negative is connected to the n-type, and at least you have 0.7 or more than 0.7, then the junction is ready to have fullest current. So are we clear? Previously you asked the junction width, is it ever going to get lower, right? So remember that 0.7 volts, we always say theoretically 0.7 volts. But when you're making the junction forward bias, you always observe that, okay, we already have electron current that is being shown here, right? But what we are also missing is, so when the electrons are going this way, what about the holes? Now, P region, you have P region here, which are very rich in holes, correct? And you have positive here. So the holes will effectively, because when this electrons comes this side, then this positively charged may try to go towards the other side, attracted towards the negative side. Because of the nature of the potentials, so in this case you have p-type, and if this very high speed electrons that are pushing towards this region, then extremely small, because also remember, is p-type means only positive? Sorry, p-type means is only positive, or are there any electrons here? Very little electrons too, meaning that some of these electrons will also be attracted, correct? They're already within the material. But what about n region? Is it only electrons? No, there are some positive too here. So this positive will go this way too, correct? But that's extremely small compared to the actual current. Does that make sense? So because of that very small current that goes this way, the depletion region will shrink extremely small. So instead of 0.7, maybe ideally you're going to have 0.69, 0.65, something like that. That's the only instance where depletion region will shrink, because of that extra electrons and holes on P and N regions that goes away. So the effective voltage barrier will reduces a little bit. So as usual, therefore, applied voltage increases, current starts to flow across the junction. As long as you reach the barrier potential, then the appreciable amount of current flow, which will happen, again, just reinforcing the voltage values needed, 0.7 volts for silicon, 0.3 volts for germanium. Again, whenever we say enough current or appreciable current, that's basically meaning that it's enough current to do useful task, not microamps or nanoamps of current. And you're always going to have that in semiconductors. But if you flip other way, correct? Remember, reverse bias means this is p-type, correct? So p-type gets what? Reverse bias means p-type gets negative, n-type gets. So if you do this, again the same explanation. So now negative is here. So the source will push an electron this way, correct? So what will happen is this is a p region. So these electrons will fill. These are all negative. This becomes negative. What about here? All the electrons in the in region will be attracted towards. So if you look at the current direction on each side, these will be attracted. So this goes this way, this goes the other way, correct? So yeah, so what happened to the depletion region now? It is getting bigger and bigger because both are going in the opposite direction, not across. So that's why there won't be any current flow through the junction as you are opposing. Pardon? Yes, yeah. As soon as you put that like that, of course electrons flows at the speed of light. So as soon as you do that, that's the actual direction, and whatever the charges that you have will be counteracted by the battery source, and you're not going to have any current through the junction. Yes. The initial junction will be like this yellow color. Like a junction means like a border between p-type and n-type. So as you keep on increasing, for example, if I keep on increasing negative voltage, this depletion region widens, widens, and widens. And it may damage the diode too. So we will talk about that later. Yeah, outwards and counteract with whatever your supply is. It will negate your supply. No, remember battery means there is no connection in between the battery. It's a separation between positive and negative charge.
Oh, okay. Yeah. When the depletion region is really small, current goes across really. Yeah, and the depletion region is bigger, it just shuts down.
Yep.
Seems like it's pointless.
Again, remember here, same exact point I'm repeating. This is the same PN junction, right? If you connect one way, it is allowing the current. If you flip the source, no current, meaning that one device acting as conductor and insulator depending upon how the voltage is being fed, meaning that it is doing automatically. It is acting as a conductor, acting as an insulator depending upon what type of voltage we are feeding in. So
the perfect example is a bridge rectifier.
Yeah, of course.
Everybody will understand exactly why it does that. As soon as you show a bridge rectifier.
It's a power supply. So in diode applications, you will see what can I do with this. It's a basis for example, if you have an automatic lights turning on, correct? Whether it could be like in your cars when outside light intensity was lower. So who's making that decision? How come a circuit that is automatically turning a light on without any manual intervention? So you see devices like this, without any manual intervention, all we are doing is flipping the polarity, which can be done through programming. So I can flip the polarity of an electrical signal. Now the device is completely behaving oppositely. Right? So that's why it's called as semiconductors, because their properties are in between conductors and insulators. I can use it as insulator if I wanted to, but the same device I can use it as a conductor. All I need to do is flip the electrical signal other way around. That's all. Of course.
How your stuff works circuit though goes from positive to negative. So if you only want the positive half, you have that diode in there. It only allows the positive half. That's all the negative voltage. Now you've got nothing but positive voltage.
Yeah. So in the applications, you will see where this behavior is more useful, right? So this is how it behaves. But maybe once we talk about or starting talking about applications, maybe it will make more sense in terms of how can I use this with. So that's applications. But like exactly he mentioned, if you have a sine wave feeding through the diode, remember part of the sine wave is positive. That's like forward biasing the diode. But as soon as it flips it, you are reverse biasing the diode. That's exactly what AC and DC is. Remember, I think I mentioned this one in our last class. Is this signal an AC signal? Is this signal an AC signal? No. Because AC means the current direction should be alternating. This one, the signal stays completely. So this is a DC signal. But it is not a DC signal that we can use because there are a lot of fluctuations in that signal. The devices could be, they're not going to work in a proper fashion because the signal is keep changing, even though this is DC or this is also a DC. Right? So this is actually a full wave rectifier signal actually. But we'll talk about this one, but this is a DC. You see the diode can actually remove half of the cycle. Right? So, but we will talk about applications down the line. What can I do with it? Yes.
So it's really quick forward bias from they're taking their both flowing inwards across.
Through the junction. Yeah, forward bias means it will go through the junction. Current will go through the junction. Again, remember we're talking about only electron flow. So these electrons will go this way. Attracted towards the positive. Yeah. The other way around is extremely small. Yeah. So that's the forward and reverse bias. So under reverse bias, the depletion region will grow in width. That's why there is no current. This causes electric field produced by the ions to cancels out the applied voltage. Ideally, we say no current. Like for example, whenever we say reverse bias, perfectly no current. But when you put it to practice, to the test, there is always going to be some current flows through called as leakage current. This is the drawback of semiconductors, and any application you take, even nowadays too, the technology nowadays too, there is always going to be some leakage current, even when you are operating under reverse bias. That means you are consuming the power from the battery or from the source you are supplying. That's not going to be a more efficient system if you're consuming power even the device is not operating, right? So you will quite often hear this term leakage current. So it's always mean that it's the unwanted current that will flow through the component under reverse bias. And you can test it too, but most of the multimeters cannot go a lot lower to like nanoamps and microamps. You may see 0 on their display. But if you have a multimeters that can test very small currents, you can actually see reverse currents. But most of the multimeters that we use, handheld ones or anything like this, if you want to test the leakage current, you need to have a meter that can actually test nanoamps because it's going to be extremely small. Sometimes it may go into picoamps as well. So this is the forward bias curve. So if you take a look at this curve, so There are some terminologies here we're gonna use. When you see your formula sheet as well, you will see these labels. When a diode is forward biased, remember that there is a current, but that current is indicated by I with a subscript of F. F for forward. With 0 volts across the diode, of course, you're not going to have any current. But if you're increasing the forward bias voltage, the voltage across the diode gradually increases. Remember that once you reach to the 0.7 volts, you can look at this curve. This curve is plotted between VF. So what do you think VF means? What is that F stands for? Forward. VF is the forward voltage. This current is drawn between forward voltage versus forward current, meaning that this curve is voltage on the diode versus current through the diode. It's not your supply voltage. It's not what you are providing. It's voltage on the diode. As you can see that below 0.7, you see the current is extremely small and gradually increasing. But once you hit that 0.7, you see the current curve is drastically increasing to whatever the circuit capability is. Based upon the voltage source and the resistance we are providing, the current will drastically increases once the voltage on the diode, again, it's not your source voltage. You need to close that barrier potential. So once the voltage on the diode reaches approximately 0.7 volts, the current will drastically increases to whatever the capability of the circuit is. But until that, you see current is not zero. It's extremely small. That's why we say it's not appreciable amount of current, because it's very small. But when you reverse it, this is what will happen. Again, you see right here, the labels are IR. You see the current is in microamps now. Whereas for the forward bias, I don't know whether you can see this label, that's in milliamps. Maybe I can remove this arrow. Microamps means that's a small. Remember that in reverse bias, there is extremely small current will flow through. So if you reverse bias the diode, you see this current right here is extremely small. So very, very small. So when a diode is reverse bias, extremely small reverse current, remember leakage current is the term they use to notify that. We can actually look at the data sheet of the diode, able to tell that. Goes through the PN junction. No, it's called as a breakdown. Breakdown. I will come back to that point in a bit. It will be somewhere here. So remember that when you're applying reverse bias, there would be no current. We all know that, right? So reverse bias means what? Okay, how can I make it reverse bias? So let's say I have PN junction. Correct? So P type will get a, and N type will get a. So we say that, let's say the voltage is 1 volt. Is there any current ideally? No. Let's say I'm making 11 volts. What do you think? Any current? Yeah. Ignoring the leakage current perfectly, is there any current? What if I put 111 volts? No current, right? Ideally, that's what should happen. But if you keep on increasing this voltage, you're already reverse biasing. Correct? If you keep on increasing this voltage, there is always a limit for that barrier to widen. But at some point, the diode will get into a region known as a breakdown region. And you should never operate, first of all, the diode in the breakdown region. But what will happen is, if you keep on going up, eventually excessive heat will develop internal to the diode and it will burn up, of course. But when it does that, you see the current, is it small anymore? It is increasing beyond the breakdown, correct? That meaning that even in reverse bias, the diode will allow the current if you go beyond the breakdown voltage.
Why do they show it as negative current? So it allows current to go through?
Yeah,
Yeah, the breakdown allows it to go through. Why does it show it as negative?
because the voltage being applied is a negative.
It's not negative current.
That's why it's a negative current. Yeah, because you are measuring, if you use the meter in the same location as opposed to forward and reverse, if you don't flip the meter, you read a negative reading. So that's why it was plotted on the negative axis. So negative current, negative voltage. Right? So it's placement of the meter. If you don't reverse the meter, if you keep the meter in the same location, either in forward or reverse, you're effectively going to read negative voltage, negative current, right?
Negative voltage.
Yeah, current will be negative as well if you go the backward direction. So beyond that breakdown, which is usually referred as, for diodes, it's referred as avalanche effect. It automatically means that you are exceeding the reverse breakdown voltage of the diode. Again, this only comes under the reverse bias. So if you keep on increasing the reverse voltage, there may be a point, because remember, reverse bias means it should prevent the current. Again, it only can prevent until so much. But if you keep on increasing it, this is another application of diode too. Not quite Zener, but usually inside the ICs, we use a diode. So for example, if I have a device, right? Let's say I have some device. Let's say this device, according to the manufacturer, this device only takes positive voltage. Right? But let's say, for example, we don't see that and we try to put negative voltage to it. So if the device does not have an internal protection, it will damage. Right? Does that make sense? Let's say I have some X device. It can only take positive voltage. But what if you go there and put a negative voltage? The device may get damaged if it does not have a protection. But what usually done is, so we put a diode inside this device. So what will happen if you apply negative voltage? So what we do is we put a diode inside. So now what happens if you put a negative voltage? What will happen to the diode? It will be reverse bias and it will stop the source. Correct? So diodes can be used as a protection devices too, to such type of applications. So if you put a positive, if it's well enough 0.7, it will simply allow it, whatever the current is. But mistakenly, if you switch it, let's say, for example, you don't know how to connect a battery. If you don't look at the polarities, or if you don't look at the manufacturer data sheet, then there may be a possibility where even for momentarily you apply negative voltage, you may cause the device permanently get damaged. So most of the ICs will be protected like this internally. So
Did you use the Zener diode to break down our voltage from the ground?
So Zener, if you know what voltage you want to use it. Zeners have a particular Zener voltage. So under chapter 3, we will be discussing Zener diodes. That's where you will see and how it is different from traditional diodes. So putting both curves together, this is the complete characteristic curve for the diodes, which is referred as VI characteristics. We will have a lab next class to actually see both of these two in the forward bias and also in the reverse bias. Again, forward voltage means this is the voltage across the diode. Forward current is current through the diode. Again, these are not your source voltages. These are primarily on the diode. So this indicates all you need is 0.7 volts. So as soon as you hit 0.7, the current rises drastically. And that's it. Of course, if you lower the voltage, the current will go down. Yeah, it's going up depending upon, remember, current is so whatever your resistance is, whatever your source is. But on the reverse bias, the current is until you reach the breakdown voltage. That's the maximum reverse voltage we can use it. That is usually given by the manufacturer as well. For the diodes we will be using in the lab, it's like 50 volts is the reverse breakdown. Of course, our supplies will not go 50 volts, so 30 volts is the highest. So you cannot see the diodes getting damaged. So if you reach to that point, let's say for example, if the diode breakdown is 50 volts, right? If you don't apply 50 volts, you're not going to be in the breakdown. Correct? If you apply, let's say 5 volts, are you going to be in the breakdown? You're nowhere close to the breakdown. Means this is the highest voltage in the reverse bias you can apply to safely operate the diode. Does that make sense? That's the breakdown voltages. Again, as I said, like the chargers that we use for our cell phones, laptops, those have like 400 volts, 1000 volts breakdown voltage. What? No, I didn't say only. So